So welcome to the new semester, and it's our first probably just taking seminar. We're very happy to have Haotian from UCLA. We will be talking about maximum Poissonian log-correlated field.
Okay, thanks for having me here. I'm Haotian. I'm a new postdoc at UCLA, mentored by Professor Mary McCart. So this is based on upcoming joint with my PhD advisor, Nicholas Cook, currently at Duke University. As the name has something like maximum, Poissonian, and log-correlated field, I'm going to first talk about what is log-correlated field and why on earth should we even care about this subject. And if we care about the subject, why do we care about its maximum? After that, I'll talk about a specific type of log-correlated field, the Poissonian log-correlated field studied by us. And of course, why do we even care? After that, I will talk about our main results and try to talk about the intuition behind our main results. Why is it new and why is it different than something previously known? Okay, so let's start. First, I will define what is log-correlated field. So you are going to define lots of random variables on a metric space that forms a random field. By log correlation, I mean their covariance is decaying logarithmically according to the distance apart from 2 points, roughly like that. So you can see when the distance between u and v goes to 0, you have a logarithmic singularity goes to infinity, which means usually you need to do some regularization to solve this issue. So one very typical example is you look at a power series with independent random coefficients, roughly of size 1 over square root k, or the coefficient of z to the k. For example, you can do a IID standard Gaussian and then divide it by square root k. That will give you one such example. If you have something like that, you compute the covariance, then it will roughly be like the expansion of a logarithmic function, and that matches exactly the negative log of the distance formula we introduced above. So for example, these random power series with coefficients decaying like 1 over square root k, they are log correlated.
Do you need a Gaussian to do this calculation or anything?
No, I just need the variance to exist to order. So there are, of course, more interesting examples instead of just power series. The first class being characteristic polynomial of random matrices. So it's well known that circular beta ensembles belong to this regime, and also includes regular matrices, beta ensembles, and IID matrices with complex entries. There are some more examples I'm going to talk about that leads to the Poissonian log-correlated field model. So I will hold on that a little bit. There are also very interestingly models from number theory side. So, there's a famous connection between random matrix theory and number theory. So you can imagine some important number theoretic functions have the similar behavior, like the zeta function on the critical line, and more recently discovered by Adam Hopper, the random multiplicative functions. And I will talk about a forthcoming work that leads to similarly the Poissonian log-correlated field. And historically, the first study on this subject might be branching Brownian motion and also branching random walk, with the idea that it kind of has a relationship with reaction-diffusion PDEs, like Fisher KPP equations, those nonlinear parabolic equations. And finally, you have lots of two-dimensional statistical mechanics models that has a log correlation structure, like the two-dimensional Gaussian free field and related models. So after all these, we may have a feeling that, okay, log-correlated field is something we care about, but why are these models connected with log-correlated field versus log correlation? So I will talk about two models exactly, branching random walk and characteristic polynomial of circular beta ensemble. So branching random walk or branching Brownian motion is you start with a family tree, for example, a binary branching. Then you add IID increments on each of the edges. On all of the exponentially mapping leaves, you define the random variables as summing over the random variables from the root, from the path from the root to that leaf. And then you can define, well, in this case, 2 to the n many random variables, and then we'll form a random field, just like this. The point that is log-correlated is because if we consider the size of, or the number of points, number of leaves that have a certain covariance with a given point, then that decreases exponentially, which is kind of equivalent to say the correlation decays logarithmically according to the distance. From random matrix size, let's say we look at a CUE, which is a hard measure of the unitary group. It's well known that it's characteristic polynomial. If you first take the logarithm and then do the expansion, it can be written as a power series with coefficients being the trace of matrix power over k instead of square root k. The point is the square root k comes from the fact that the trace of the matrix power is typically offset square root k. After taking out that square root k and divide your traces by that, they will converge to IID standard complex Gaussians. So we can safely say we can replace trace of this unitary power over square root k with IID complex Gaussians, and we have something like this GC of z over here. It's a log-correlated complex Gaussian. We know it's log-correlated from the first slide we've just seen. The coefficient is IID Gaussian, IID random variable divided by square root k. And for example, if we just care about the real part of it, it will be a random Fourier series. So we've been seeing branching random walk is the log-correlated field, and this characteristic polynomial connects with the Gaussian random Fourier series. It's possible that, and actually it's the very important tool in this field is in the subject of study, is that you can find a branching structure analog out of this random Fourier series. If we take a look at this Gaussian field, we want to first fixity write it as a random walk. So for that, we need to find O1 increment at each step. But because, oh, I'm missing a square root j over here, sorry. But because the size of the jth one is 1 over square root j, it has there as 1 over j. So you need to group exponentially many such term to have an O1 increment. So we we partition the summation into these exponentially growing boxes, which means there are only effectively log n number of steps in running fixed t. And we call each single step little sk of t. So here, I'm saying here, I'm missing a value by square root j. Each single step sk of t, they are of order 1. They are independent for different k, but they are correlated for different t and s. And we're going to talk about what are the correlation structure. So we make the computation. In this specific case of Fourier series is computable. So you can see there's a transition from constant order to rapidly decreasing, exponentially decreasing actually. For k that's crossing a criticality negative log of the distance between t and s. So from this, we can read two facts. For one thing, the two fixed pair of leaves, a pair of two leaves, T and S, they kind of branch at generation K, which is roughly this negative log T minus X. And also at each level K, you will need like a e to the K number of points on the unit circle to approximate the original random Fourier series. Because when the distance between T and S is smaller than e to the negative K, they are strongly correlated. Usually they behave like the same, which means they're sharing the same increments. And after, when the distance is larger than e to the negative K, there's some partial steps that gives you independent increments. So that means they have branched since that level onwards. So that's all about what log-correlated field is and what kind of models will give you this log-correlated structure. And also when you have log-correlated structure, you would expect a branching structure from. Now I'll briefly talk about why do we care about maximum and what do we know about the maximum of log-correlated field. So the very first story is from McKing, that he linked the tail of the maximum of a binary branching Brownian motion to that of to a traveling wave solution of the Fisher KPP equation. The point is, if you look at UTX as the probability that your maximum at time t is greater than x, it solves the nonlinear parabolic equation called the Fisher KPP equation with the initial condition like this. Then it's well known in the linear PDE literature that after t is greater than 1, when the solution evolves, it will look like a traveling wave with some given speed moving to the right. So, for example, one major question is how large is this t in terms of t? And what is the shape of the solution when you just move this, get rid of this linear or roughly linear growth of mt. So that is being similar as asking what is the typical size of the maxima of a binary branching Brownian motion, and what is the shape of the tail of this maximum. Another motivation is the maximum, because lots of statistics mechanics model have a log-correlated behavior. We can look at the Gibbs measure constructed from these kind of models, and the free energy from that is closely related to the maximum of these log-correlated fields. Because if you want to have a very low temperature, and those are only going to, the Gibbs measure is only going to be supported on the maximum of the. So to solve this question, Bramson and then Zeitouni derived the following result. The maximum is roughly of the size square root t minus 3 over 2 square root log t and plus some constant term. Then later on, Lally and Zeitouni proved to converge in law to some non-trivial distribution. It's important that first you have a linear term, and then you have a log t correction to that first linear term. The second term is called the Bramson type shift. Then in 2012, Fyodorov, Hiary, and Keating, they motivated from the connection between random matrices and analytic number theory, and also a connection to statistical physics. They used some random energy model to compute what is the maximum of characteristic polynomial of circular ensembles and the maximum of Riemann zeta function on the critical line. They made the following very precise conjecture for the characteristic polynomial. The maximum should behave very similarly to the maxima of the branching random walk or the branching Brownian motion. If you take out that square root 2 from the first term, that will give you coefficient 1 and -3 for exactly as conjecture. They even have a very precise conjecture for the limiting distribution of the third term xn.
So the xn is random, but this Bramson term PDE is different.
No, it's also random. You will converge in some non-trivial distribution. It's roughly the sum of independent gamble and another independent random variable. So in the FHK conjecture case, another distribution is also gamble. But in general, for branching random walk or branching Brownian motion, we don't know what the distribution is. We have some descriptions, but we don't know what exactly it is. So first of all, Argon, Belius, and Bourgat in 2017, they figured out the leading order. Then Paquet and Zeitouni figured out the subleading order, the Bramson correction term. Taibi, Model, and Nachiludo figured out the tightness of the xn term in the same year, and pretty recently, Paquet and Zeitouni proved the convergence in law of xn. So they at least show it equals to the sum of one gamble and independently another random variable. And in perfect communication, they say they know how to show the other random variable follows the gamble distribution. So kind of the FHK story from the random matrix side is resolved. So later than that, there's some universality result established for random matrices for Wigner and beta ensembles. Bourgat, Lopato, and Zeitouni established the leading order and used that to show optimal rigidity for the eigenvalues. Then Cipollone and Lennon in 2024, they study IID matrices with complex entries. Those papers show the leading order asymptotics follows that, but not follows, just have the same behavior as the maximum of CUE. In the IID case, the model is a little bit different. You will have one covariance in the first half of the growth, and the second covariance in the second half of your random walk. So there's one transition between the variance of your random walk. But overall, the big picture for the leading order is this. That's from the number series. And also there's a okay, I should modify this. Also, there's a story on the number series. So as I mentioned, FHK made a very similar conjecture for zeta function on a high but short interval. So you can see here it's high because you first look at the critical line, the real part equal to 1/2. Then you look at the high point little t, which is taken uniformly in between a large t and 2t. So you first randomly pick a high point, and then look at a short interval around it. So you take h to be smaller than 1 and larger than 0. You consider the maximum of the zeta. Then the idea is, in number theory, you will roughly translate any n to log t. So if you replace n with log t, then you have the same limiting behavior. So the most recent result on this is by Agan, Bogat, and Radsville. They showed that yt term is tight, and also they have a uniform tail estimate of yt, and that tail estimate matches the conjecture distribution of the limiting.
And why is the conjecture? They already proved the tail. Is it still open for the first two terms?
No, the first two terms is already proved, and we also know yt is tight, so it's of order 1. And also know the tail of yt is the same as the conjecture distribution.
You want to get the distribution?
Yes. We don't have convergence to the exact conjecture distribution yet, but we know the tail matches at least. So we are off by roughly some multiplicative constant and something like that. That's the most recent study on the number theory side of FHK conjecture. Because this is not the focus, so I will not talk about the other literature on this side. That's part of the maximum study literature. Now I will talk about why we care about Poissonian logarithmic field. Am I going too fast? I think it's fine. Any questions so far before we go through the model we study? Okay. So instead of circular ensembles, which is a dense matrix, we instead look at sparse matrices. And we start from a very simple sparse matrix, a random permutation matrix. So first you take a random permutation, then you construct a matrix out of it by allowing ij's entry to be 1 only if the random permutation permutes I to j. So you can imagine in an n by n matrix, there are only n non-zero elements being 1. The rest, most of the elements are 0. It's a very, very sparse matrix. If we decompose the log characteristic polynomial of this matrix, so first of all, the random permutation will consist of lots of loops. So we can write the characteristic polynomial into a decomposition of these loops. You have this 1 minus d to the L if you have a loop of length L. And that will be repeated CL times, which is the number of loops or circle of length L in your random permutation. Then we take the logarithm of this product, gives you a summation, and this number of length L cycles becomes the coefficients in front of log function. Okay, and Russia and Tavale once showed that jointly you can replace these number of cycles of length L by independent Poisson random variables with coefficient 1 over it. So just this very similar to what we do in the CUE case. You replace the trace of the unitary power with Gaussian divided by Gaussian times root k. Here we don't have any other root k. You just replace CO by Poisson. So after doing that, you will have a random function series. F of LT is log, is some kind of log function, and you will have a random coefficient ZL being Poisson 1 over L. So I will mention this is also log-correlated. It's not of the side of the shape O1 random variable divided by root k, but still, if you consider the variance of this, it gives you a 1 over L or 1 over k. So as long as you have a variance 1 over L for each term, you will have a log correlation. But the point is, although they have the same order of variance, for any nk over square root k, it's almost guaranteed, it's almost surely non-zero. For any k, it's a meaningful term in your summation. Here, you don't have this 1 over root k. Instead, you have Poisson 1 over L. Well, L is very large. It's very unlikely for your Poisson to be non-zero. So instead of having every single term being effective, you only have log n many of effective terms. And there will be lots of zero, some ones, and you almost will never have 2 or even higher numbers. So there are other sparse matrices that looks like something similar, like there's study on sparse random recurrent digraphs by Coase, Lambert, and Ijadu, and also their study on sparse IID Bernoulli matrices. They show that the characteristic polynomial of these sparse random matrices will look like something similar to the exponential of this Poissonian field. So not exactly the same, but something similar. This is from the random matrix side, why we care about Poissonian locally field instead of a Gaussian. There's also a story from the number series side as well. So in number series side, people care about something called twisted divisor function. You first consider all the divisors of integer n, raise the power to IXC. It is the Fourier transform of the point measure supported on log of the divisors. So for example, you can imagine you can retrieve information about divisors from this function. And in the famous textbook of Hall and Tenenbaum in 1988 called Divisors, we asked the question, what is the asymptotics of maximum of this absolute value twisted divisor function on a short interval C in 1 and 2 as n goes to infinity? And that question is still open. But in a forthcoming work, Argan, Bogat, and Kokolopoulos are trying to answer this question with a random model. So instead of asking n to go to infinity deterministically, we just pick a random n from 1 to x, and then x goes to infinity. The nice thing about this is we can do decomposition of log to the twisted divisor function tau. So for example, let's look at a simple case. Well, n is square free, we can rewrite tau in terms of product over all of the prime factors of n, because there's no square of the prime. It will equal to exactly 1 plus p to the x. If it's not square free, there will be extra terms, p to the 2xz and so on, to how many prime factors you have over there. But the point is, for all of those higher powers, you can expand this product, and those higher powers will give you something negligible compared to the mean term. So let's focus on the square-free case. Because we are taking n uniformly in 1 to x, it's a very famous number theory result that the probability for a prime factor to be in such an n is roughly independent and have distribution Bernoulli 1 over p. This is the so-called Kublius model in 1964. Which means instead of considering all the prime factors of a fixed n, you consider all of the prime numbers smaller than x. and P divided by N means whether it belongs to the prime factor of N or not. And that is modeled by independent logarithm graph. So if we take logarithm of this, you have summation over a logarithm 1 plus Bernoulli times PIC. When this Bernoulli equal to 0, the logarithm equal to 0. So actually we can take this Bernoulli outside of the logarithm. You get something like summation over Bernoulli 1 over P times log 1 plus PIC. This looks very similar to the log-correlated polynomial of sparse matrices. You have something with a log singularity over here. It has no randomness. It's just a log function. And you have independent random coefficient that is with probability 1 over P will be 1 and probability 1 minus 1 over P will be 0. Because Poisson 1 over L will have negligible probability for being greater than 2. You can imagine these two models are actually looks pretty much the same. So this is from the number theory side, why we care about Poissonian log-correlated. But the fact is, these Poissonian fields are too hard to study. So instead of studying them directly, we propose some modifications to the models. And still, after all these modifications, it will still look different than the Gaussian model. The first result on maxima of this field is by my advisor Nicholas Cook and Alfred Zeitouni in 2020. They studied the leading order of the maxima of log characteristic polynomial of random permutation matrix by using that Russia-Turale result to replace counts of circles with independent Poissons. With that result, the leading order they get is some constant times log n. So the scale is the same as the Gaussian fields, like for CUE, you still have log n order, but the constant is not 1. It's something C0, which is roughly 0.652. The reason why that is different is because in this case, you no longer have a Gaussian tail for any fixed point t. You still have COT. If you fix the t after a certain scaling, that distribution still converges to Gaussian. But if you look at the large deviation, look at the tail, it has a non-Gaussian tail. And especially in this case, it has a Poissonian tail. So that makes the constant different that way. There are several comments on their work and on their results. So this is the one I just mentioned, C0 not equal to 1. It comes from the non-Gaussian tail and large deviation scale. And one technical difficulty is the f function is the log of this 1 minus e to the x. So it has a singularity pointing down to negative infinity. So you certainly want to avoid that when you want to study the maximum. You need to do some cutoff, and especially if you want to establish a lower. Another difficulty is this field is no longer rotationally invariant, unlike for CUE. You need to do some treatment as we will do for the next comments to make it roughly or asymptotically rotational invariant or stationary. The last and the most significant technical issue is this field has a very complicated and number theoretic correlation structure. You can imagine if we take a look at this term log of 1 minus e to the 2 pi I LT. And the log of 1 minus e to the 2 pi I LS. You can rewrite the first one with the t terms, which is 2 pi I LS times e to the 2 pi I L times t minus s. So if t minus s is close to a rational with a small denominator, for example, 1/2, you will have lots of L's that this term is roughly 1. Which means even when the 2 points T and S are very far away in the global way, they are strongly correlated. Because for lots of L's, for lots of summations, you will have strong correlation. this is not an issue in the Gaussian case because you have so many summations. Every L is effective. So that universal, or not universal. The huge number of L's kind of cancels out this behavior. Here in the Poissonian model, we have very sparse support on L. So in this case, the problem becomes very problem because just not negligible. And so in their paper, they spent a huge amount of work on number theory to deal with this issue. They finally figured out that the maximum is obtained when TNS is actually not close to any rational with a small denominator. So in number theory, they call that the minor arc. So they just show that if you fix the T and look at the related points, then the maximum is supported on minor arc. Okay, so those are technical difficulties even for dealing with the linear order. So because of this, we propose a cleaner model. Hopefully still capture the most important thing, that the support of the future coefficient is sparse, but we want to get rid of the number theoretic factor. We want to get rid of the log singularity, and we want to get rid of the non-stationarity. So if we first do one thing, we notice that those Poisson's ZL are very unlikely to get larger than 2. So you will either have the L here, or you will have one L over there. Poisson will either be 0 or 1. In that case, you can model it by a Poisson point process with certain intensity function on integers. Then the summation over a Poisson times this log function, or this f of LT. You can just model it by summation over all of those effective number of L's, and that will form a Poisson point. That's the first step. The second step is, as I just commented, the maximum is obtained on minor arcs, and when the point T is very irrational, and you are not going to approximate any integer by multiplying over integers, then they will quickly equidistribute the unit square, because this trajectory will never end into, or will never be close to one another. So in that sense, you can think about LJT for large J as roughly being uniform over 0 and 1. And because of that, it also kind of suggests that the maximum is staying away from the log singularities. So the log singularity really does not play much important role in the study of maximum. So you want to maybe get rid of the singularity and assume the function is bounded. That is another modification we will do. So we introduce the following model. To fully get rid of the number theoretic object, we then replace this LJ with a continuous subject, the exponential of Poisson arrivals. So they will behave very similarly. If you round up this e to the exponential of Poisson arrivals in integers, you will get LJ. After doing this, we are working on a continuous time model. So we will no longer have any number theoretic behavior. Then we will replace the function f with something very nice, for example, bounded and smooth. So in this talk, I will focus on f being cosine, but actually we can allow for more generality. And finally, last but not least, we make the field stationary by adding a IID uniforms to each of the element LT. So LT itself is not rotationally invariant, but after adding a IID uniform on 0, 1 random variables UJ to it, now the field is stationary on the real line. The very last modification we made is in the previous model, we are only counting all of the Poisson point process that with points smaller than a fixed number of elements, n being the dimension of the matrix. But that means there will be a random number of steps in your random walk, where this summation over j, the number of j's is random. So which means that we will have somehow like a random walk bridge, and that will be very technically involved, as I will explain later. So instead, we fix a fixed amount of time, fixed amount of step of n, little n, to our random. Now, there's no number theoretic correlated structure. Our function is very nice, bounded, smooth, and periodic. We have a stationary random field, and we have fixed number of steps. Everything seems so nice. We've just gotten rid of most of the nasty part. But what we actually discover is after all these modifications, the maximum behavior still is super different from the Gaussian logarithmic. So here's our main result. Our main result is the maximum of this modified model, the cleaner model, will have, of course, first the linear term, C1 on constant C1 times n. But then we will have a second term as C2 times the nth Poisson arrival. This term does not appear in any Gaussian model studied before. And if we condition on this random Poisson arrival process Vn, we will have a third term being log n. It looks like the Bramson type shift in previous Gaussian and nearly Gaussian models. But the point is the C3 is very different and comes from a different mechanism than the Gaussian models.
Why do you call Vn the second order term? Is it bigger than log n?
Yes. So you see the Poisson arrival is the sum of n IID exponential 1 random variable. So first you will have leading order n, and then you will have a second square root n order fluctuation. So the leading order is given by the first two terms, C1 plus C2. And in the random permutation model, C1 C2 will be exactly the C0. Cook and Zeitouni figure out. The most different part is, in this case, the maximum will have a CLT behavior. Because of the existence of Vn, the maximum will have a square root n fluctuation. If you modify this, the maximum will converge to a standard normal distribution. And the C3 comes from a kind of different mechanism from the Gaussian local field. It's also no longer 3/4. And I will explain this later. So, is there any question? Yes, dive into explanation. Okay. So the explanation is majorly just why we can view this Poissonian field as a branching random walk model. The idea being that, first of all, it is a random walk with bounded increments. Each of these cosine of 2 pi kind of elements, they have no longer a 1 over square root k modification in front. They are of order 1. So we have O1 increments already. And also there are Lipschitz in the argument T. The Lipschitz constant is roughly the summation of the exponential to the Poisson arrivals. So with high probability, you go up to polylog n, e to the nth Poisson arrival. So you have population size of e exponential of the Poisson arrival at time n. For one thing, the population size is random. So we would expect each time you would sample a number of children, e to the vj minus e vj minus 1, as the number of children for each parent in your next generation. Remember, here you sample it to be 3, and then maybe the next sample is 2. So everyone will have 2 children, so on and so forth. First of all, the branching law is random and time-inhomogeneous. This is what we call random and time-inhomogeneous branching. And because of this, we want to quench the Poisson arrivals V completely. And after that, we have a deterministic branching loss. But this actually fails to provide us with a decorrelation structure between two different points. Because at level J, if Vj is completely fixed, they act for the increments at T and S, they share the same Uj. So there's no independence left for you to have any decorrelation between points T and S. So to solve this question, we need to fix still roughly the Poisson arrivals, but only where it fluctuates around. So we will look at the rough position of Poisson arrivals, but still allow it a little bit length of row range to fluctuate. It turns out that this small fluctuation is enough for us to have decorrelation between the paths and therefore to prove asymptotic independence. So after that, we got a branching structure. We actually have a tree structure in the family. So this kind of branching random walk is called branching random walk with time-inhomogeneous branching laws, or branching random walk in a time-inhomogeneous random environment. It's first introduced by Beans and Cipriano in 2004, and later on studied by this group of authors. The latest result is by Krishnan in 2025. They obtained tightness in the maximum. So the most important part of the proof is if you want to count the maximum of branching random walk, we kind of want to count the number of points attaining a high point. So first of, for example, for the leading order, it comes from the trade-off between the population size 2 to the n and the tail estimate as a Gaussian tail, for example. You solve this equation to find the balance between the exponential growth of population size and the exponential decay of the tail. You find the leading order to have that exactly shape. The problem is if we want to continue this first moment approach to the sub-leading order, we will have the trouble. If you sit down and work out this Gaussian computation, that will suggest an upper bound of in the log n order, but with a different cost. This is actually higher than the correct maximum. That is because by first moment method, you forget everything about the correlation structure. So actually the correlation between different paths drags your maxima down a little instead of for IID Gaussian box. That gives -3. So that's because we're often counting lots of points. If you count all the high points, then it's possible that one very high path at the beginning of the process will give birth to exponentially many offsprings at time. If you consider the maximum, then you will count lots of offspring that just comes from one parent early in the generation. We want to get rid of this case. We want to say just don't have those exponentially many kids. Maybe you just count one kid per family. One way to do this is introduced by Bramson by adding a barrier to this counting. So instead of just count the number of points above a high point, we'll assume that you will never cross a barrier. So this solid linear line is roughly the linear speed in the leading order. We raise it a little bit to the dashed line as a barrier. We only count the family, we only count the trajectories that never cross this barrier and end up as a high point. So we fully get rid of this possibility that you will go very high in the middle and then give birth to lots of truth. So after doing this, you have a linear drift barrier. We can do Giordano check barrier to get rid of it. It left out with a very standard probability. Your random walk will stay below a fixed, will stay below a fixed number and end up in a short interval. This is a so-called battle theorem. You want to never go above a certain line. By doing that, you will get an n to the -3 hat, which is a battle theorem probability. And by doing Giordano, you will get n to the C0b. So the correct B to balance this probability is -3 hat over C0. And that's where the 3 hat comes from. In our model, the branching or the population growth is random. You can see here in the linear step is actually there to balance the population and also the tail of the random walk. So if your population is random, you need also a random height and of your random walk to balance that population groups. So we need to replace this k by C1k plus C2vk to correctly balance out the population groups. But vk is random. So in this case, we are actually doing a different balancing. First, you will have a random walk generated by Poisson arrivals V. And then you ask what's the probability when quenching this barrier that another random walk always stay below this random quenched barrier and end up in a short interval. So this is the most important object in the study. This is developed by Malin and Milosh, so they prove the existence of the exponent in the probability. So this probability will still decay polynomially. The exponent will exist almost surely in the limit expressed by a function gamma. And this is so far what we know about this function gamma. We only know it is symmetric, it is convex, and for non-zero beta, it's larger than the 1/2 coming from the standard balance here. We don't know much about the behavior of gamma. Okay, so as a summary, we talked about log-correlated structure. It's kind of universal. If you go from dense random matrix and look at character polynomial, you will get Gaussian log-correlated field and really get some kinds of universality in that field. From Gaussian log-correlated field is analog to homogeneous branching random walk, or the most standard type of branching random walk. If you go instead from sparse random matrices, you will get this new Poissonian log-correlated field. And this new model is related to a time-inhomogeneous branching random walk. The branching law is random and time-dependent. For this maximum, we need to consider a quenched random barrier and a quenched balance zero instead of standard balance. There are, of course, lots of questions since this field is very young. First of all, even in branching random walk case, we don't know the convergence input. So far, we only have the tightness. And we worked out the cleaner model, but does that apply to the maximum of random permutation matrices? That will be a natural next step. And do we have any universality in this case? Does our result extend to other sparse matrices or the twisted divisor functions? And finally, and I want to raise to your attention the result of Malin and Milosh. So they conjecture that the gamma function I just talked about is strictly convex and at infinity should grow quadratically. But first of all, we don't know any of these two, they're still conjectures. And secondly, we don't have any guess when beta is close to 0. This is a conjecture when beta is very large. And we talked about the Poisson field. And that's a log of the characteristic polynomial. It's natural to ask, without taking that log, or like an exponential of the Poissonian field, what does that look like? So that will be something called Poissonian chaos introduced by Coase. And not much properties known for that now. Okay, thanks for listening. And
Okay. Will you get a gumbo term in this expansion? Because they have deterministic term plus a gumbo. Would you expect the same gumbo term will appear in the third order term?
I would at least expect one of the random variable will be gumbo. So the two gumbos basically comes from the mechanism that in a branching, you first will have lots of families. The first gumbo comes from the fact that you will your family should stand out among exponentially many families. So that extreme process gives you a gumbo. Then if you're in the extremal family, you should win over all your assembly. So that localized maximum will give you a second gumbo. So I would expect at least one of the mechanisms is the same. But there's currently no conjecture on what the next step is.
Okay.
And actually the tightness is obtained when the third order is not logic. So what we have for partial random walk is you subtract the maximum by first C1n and then the C2. Let's still use Vn, although of course the partial random walk have a different notation. The third term is actually C3 times log of the ballot probability. So if we keep this one without expressing it in terms of log n, we have the next term is time. But we don't know much about the fluctuation over here. If you want to express the third term as negative C3 log n, from here you will have an epsilon log n fluctuation. It's from the Malin and Milosh result. You can see here we have the convergence when divided by 1 over log n. So we don't know more about the error term. So if you want the third term to be log n, then the best you can hope for right now is log n. And I think this is very reasonable because there's some randomness in the equation.
If no other questions, next section will be very clear.